All right, this is class note C in lesson 1. Let's take a look at what we're being asked to do here. First one is to translate Newton's law of cooling into a differential equation, and then we're going to want to classify the ODE that results. So let's scroll up a little bit to talk more about what Newton's law of cooling is, and that's really contained in this statement here. And what I'm going to do is underline the most important parts of this quote that jump out at me as we try to create the ODE from it. So let's read through it. The rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature. So everything I've underlined is part of what we are going to translate into math and will then form our differential equation. So the first step here is to define variables. We are trying to come up with a differential equation, so that models the change in one quantity and relates it to itself, possibly in other quantities. So we're going to need some variables. Things are changing in this problem. So if we go back to the statement, there's definitely a temperature that's changing, and it's changing with respect to time. So we're going to introduce a T of t here, and that is going to be the temperature of the object at time t. I'm not going to prescribe any units here for the temperature or time. We can do that later as we look at specific real-world contexts. The second thing that I'm going to introduce as a, not really a variable, but a parameter here is this phrase that we see here, ambient temperature. So that's not really a variable. It's not going to change during the course of the problem, but you can certainly apply the model that we will derive to different settings with possibly different ambient temperatures. So we will denote that ambient temperature by T sub A. Great, so we have these two elements now, and let's go back and see what the statement of Newton's law of cooling tells us is the relationship between the two. So when we read the first chunk here, the rate of change of the temperature, right? We're thinking instantaneous rate of change. We're thinking calculus. So we're thinking here the derivative of the temperature with respect to time. Great. And then we read this next phrase is proportional to. So let me just pause here and go to the first page of the practice problems. This page has a link to a refresher on the terminology is proportional to, in case you need that. But long story short, going back to where we were, when you read that something is proportional to, what you're being told is that that quantity, in this case, the rate of change of the temperature, equals some constant times the thing is proportional to. So that's the long story short of what you'll find in that Wikipedia link to proportionality. And what is it proportional to? So in this case, we're told it's proportional to the difference. So I'm going to put a minus sign there. The difference between its own temperature, right? So that is what we have denoted by capital T, and the ambient temperature. So that's what we've denoted by T sub A. Great, so this is our tentative model, and I'm going to copy this to the next page. And you might be wondering why I'm saying this is the tentative model, and I'll mention that in a minute. So let's first copy down, so first step here that we were doing, the ODE. Let's copy down this model here. Okay, it's our tentative model. Why is it a tentative model? Well, we want to think about whether this in fact does model the situation that we are after, which is Newton's law of cooling. So let's run through a simple example. Let's say the ambient temperature is a room temperature. So 76 degrees Fahrenheit or so is about room temperature. And let's say we're talking about a coffee cup. Maybe that's at 120 degrees Fahrenheit. So you take a hot coffee cup, you put it, take it off the coffee burner, and you put it on the table in your kitchen table or something. The difference between these temperatures is positive. So this term here in the ODE is positive. Now let's assume K is positive. Okay. Then what would happen? Well, we would have a positive number times a positive number would give us a positive number here. So let's think about what that means. That means that if I were to graph the temperature as a function of time, then this would have to be an increasing graph. Why? Because I have a positive derivative, right? You might remember from calculus that the derivative being positive tells you that the function is increasing. This is a little bit of a problem, right? Because in this situation, excuse me, I set things up so that the difference in temperature was positive. If I assume then that K is positive, then I have this nonsensical statement. If I take a hot coffee cup, I put it in a cool room, then the coffee gets warmer. That is certainly not what happens in the real world. So again, this happened because of this assumption that we made up here. I assumed that K was positive. So there are two ways to fix this to make sure that we are modeling what we want to model, which is cooling. The first way to fix this is to go back and leave the math as is and just require that K be negative. Again, for cooling. That's what we're trying to model. The second way to fix this is to build in the fact that K is negative for cooling by putting this minus sign here. So we are going to finish this off here, T minus TA, and then require that K is positive. Again, we are talking about cooling. So both of these models will be completely equivalent, but I'm going to have a slight preference for this one. The reason being that we're used to thinking about positive numbers just a little more than we are used to thinking about negative numbers, right? We worked with positive numbers longer. So I'm going to stick with this model as the answer to our part number 1. And then let's go to part number 2 then and classify this, figure out what type of ODE this is. Okay, so to figure that out, first thing I'm going to note is that this is a first order ODE. Why? Because the highest order of the derivative in this equation is 1. Right? There are no second derivatives, third derivatives. It only goes up to first order derivatives. Great. So now that we know it's a first order ODE, we want to figure out if it's linear or not. To do that, I'm going to start multiplying things out and try to put this into the standard form of definition 1.1.1. And I will scroll up soon to remind you what that is. So here we are doing a little bit of algebra. Excuse me. Great, so we have it in this form, and we're going to compare it to the standard form of a linear first order ODE. So I'm just going to write this here. Okay, and then let me remind you where that is. So on the first page of the notes, here is what I'm comparing this ODE to. So this little bit right here. And remember what we did to try to compare ODEs to this in the first class notes A of this lesson. We tried to get the dependent variables all on the left-hand side. In this case, that was y. And then we tried to see the peculiarities that we talked about in that class notes, right? Is y appearing linearly? Is dy over dt appearing linearly? Are the things multiplying y only functions of t? And is the right-hand side only a function of t? So all of that is what we are going to do here for our Newton's law of cooling ODE. So we can compare these two pretty directly here. We see that t is like our y, right? Makes sense. That is our dependent variable. And little t here is our independent variable. That's the same. Great. And the function that is multiplying t here, which appears linearly as y does over here, is therefore our a of t. So a of t. And then everything else on the right-hand side is b of t. So indeed, this is a first order linear differential equation. Now comes the question of homogeneous or non-homogeneous. So to answer this question, we are going to look at the right-hand side. So b of t in this case is k times t sub a, right? So the answer to our question of homogeneous or non-homogeneous is actually it depends. And that is the best and most accurate answer. Why? Because if b of t is 0, then it's homogeneous. So if kt sub a equals 0, then it's homogeneous. If not, then non-homogeneous. And let's just talk through a little bit of the situations in which you might have one or two of these cases. So what would it mean for this product to be 0? Well, two possibilities. Either k is 0 or t sub a is 0 or both. And let's think through that. So k being 0, what would happen there? Well, if k is 0, right, we go back up to our model and we would look over here on the right-hand side here, and this entire term would be 0. So the derivative would be 0, so the function would be constant. So if k is 0, what's happening then is you have a constant temperature. Again, that is not a very interesting model, right? You might be taking a coffee cup and putting it in an environment that is at the exact same temperature as the coffee cup. Well, the coffee would neither cool down nor heat up. It would just stay constant. So that makes sense. What if the ambient temperature is 0? So down here, right? So that may also happen. So you might, for example, take out your coffee cup and you might be somewhere in Antarctica or something, right? Where the ambient temperature is 0 degrees Fahrenheit, right? Or just maybe a really cold day in Boston. So that may also happen. So that would mean that the ambient temperature here is 0. And then this differential equation would resemble something that we have solved before. It would look like a decaying exponential function. So the temperature of your coffee cup based on this model would decay exponentially, right? The solution here is initial temperature e to the minus kt. Okay, so again, those are just some of the things that may happen. And all of these, as I just, tried to illustrate, are possible from a physical perspective. So we do not want to rule anything out from a mathematical perspective and say, no, this is always homogeneous or always non-homogeneous. The answer really is that it depends on the parameters k and t sub a and whether they're 0. So that does it for class notes C, and we will pick up the story with the next class notes in the next video.